2 is actually the last HL portion we're going to be doing, but I split it into 2 videos because it is very big. And so it is entropy and spontaneity. And this video is going to be looking specifically at entropy first. What is entropy? Entropy is the degree of disorder of a system. So energy and matter tend to disperse, and the universe becomes more and more disordered. So we go from big, complex items into much smaller, more dispersed items, and energy is going to be released into the system or into the surroundings. Sorry. What about spontaneous change, like spontaneous combustion, right? No, this is not going to happen. Well, spontaneous change occurs without the need of work. And so the second video is going to be looking at spontaneity and how do we calculate it? At what point does something become spontaneous? That there's just free energy available. And so when we look at entropy, we can actually quantify the degree of disorder of a system, and we've applied a value. And this value represents the distribution of available energy among particles. So when you have low entropy, right? You have a very ordered system. And then things tend to go towards chaos. And this is a part of the chaos theory, right? Time occurs. So you clean your room, time occurs, you don't try to restrain it up, and over time, you get high entropy, right? It becomes disordered. Now your room's a mess, and your mom is mad at you, right? Okay. And this is the widest energy distribution that the system can have. And in order to go back into an ordered system, you have to put work in. So everything has a natural tendency to go in one direction. So as I said, entropy wants to go in one direction, and it's an increase in entropy that is favored. And this is explained by the second law of thermodynamics, which is probably one of the most important laws of science there is, and one of the least understood or misrepresented. It is the entropy of an isolated system never decreases, so it never goes backwards, it never becomes more ordered, because isolated systems evolve towards thermodynamic equilibrium, or a state of max entropy. All right, so it is a point of equilibrium. So it's not like complete disorder and chaos. It goes to a point where it's some chaos, some order. So if you look and think of your room, right, and you have it cleaned, and then over the course of the week, it becomes a mess. But things are still sort of in place. It's not like everything threw up everywhere and your drawers are completely empty. Even if the clothes aren't in the proper drawer, there's probably still things in the drawer. And so you're finding this equilibrium point that you can work with. So let's look at some system changes and figure out which way is entropy going to go towards. Phase changes or state changes, right? So if we are going to go from a solid to a liquid to a gas, all right? So we're going from order to less order to much less order. So what is that going to do to entropy? It's going to increase entropy. So entropy is going to be positive, right? Think of the reverse, right? So gas to liquid to solid. So you're putting things back more in an ordered state, so you're going to decrease entropy, and you're going to see a negative value for that delta S. What if you dissolve and you create an aqueous compound? Okay, if you create an aqueous compound, so you take a solid, dissolve it in water, well, that solid is now separating out, that water is separating from each other, therefore you're increasing entropy, and you're going to have a positive value. Temperature change. Okay, so if we are going to decrease temperature, we are allowing less energy in the molecules. They're moving less fast. They're going to have more attraction to each other. Therefore, you are going to decrease entropy, and it's going to have a negative value. Vice versa for increasing temperature. Increased temperature, increase the average kinetic energy of the molecules. They are moving faster. They're moving more randomly. They're breaking their IMFs. Therefore, entropy is increasing. Type of molecule. So you have a complex molecule like glucose, C6H12O6, right? When it's complex, you have a decrease in entropy because you have to have a lot more order to keep all those atoms together. But let's say you break that glucose down and form CO2 and water. Those are simple molecules. Simple molecules are increasing in entropy and therefore have a positive value, and that's where you're getting your energy from when you're eating food. Moles of gas. All right, so gas, of course, as we saw over in this phase change, gas is going to be the one that is more of the disorder side. So if we increase the number of moles of gas, you're going to increase the entropy. And it's going to become, you're going to increase entropy and it becomes a positive value. If you decrease the moles of gas, that means something's going towards a different phase change. Therefore, you're decreasing entropy. Number of particles. The more particles present, right, the more interactions you're going to have. So if you're going to increase your number of particles, you're going to increase your entropy, and it's going to have a positive value, and vice versa on the other one. And then pressure. Remember, pressure only affects gases. So pressure on a gas. If you are going to decrease the pressure, there's less pressure on a gas. The gas has more room to move, more room to spread out, less interactions with each other. You're going to increase your entropy and have a positive value. So absolute entropy, what we're going to be looking at. And this is where we get our standard state, essentially. So this is measured off of a perfectly ordered crystal at 0 Kelvin. Granted, we have not gone to 0 Kelvin, but theoretically we have an idea of what should happen at 0 Kelvin, right? So we say anything above 0 Kelvin, you're going towards disorder. Makes sense. And so the numbers that are produced for S, and you look at your reference tables in your data booklet, and it's reference table 12. So the numbers are always positive because real substances are not perfect crystals. They're not at 0K. So they're always going to have a positive value when you're plugging it in. Now your end result is just representing the direction entropy is occurring. So we'll look at that in just a minute. The unit, and because we love it and they love to confuse us, is joule per Kelvin per mole, not kilojoules. Okay? Kilojoules, as we've seen with delta H, everything always ends in kilojoules. S is in joules. So when you put H and S together, you need to make sure you're in the same unit, and we'll discuss that in the next video. Something to keep in mind is that entropy is temperature and pressure dependent, right? Because temperature, as we discussed on the previous slide, is increasing or decreasing the average kinetic energy of particles, therefore increasing, decreasing the amount of interaction that is occurring, therefore changes entropy. Pressure on a gas changes, again, the interactions of the particles in their gaseous state with their attractions or to each other. So we need to make sure that temperature and pressure are held consistent when looking at entropy. All right, so let's do some calculations with entropy changes. So we're looking at delta S theta. Guess what? Same thing as delta H of formation. We're looking at the summation of your entropy of your products minus the summation of the entropy of your reactants, right? So the calculation hasn't changed. This is what numbers are you using? Okay, so we are going to have C2, H4, plus H2 makes C2H6 gas. Okay. Now, before we actually do the calculation, let's do some predictions to make sure we're going to be correct. So on our reactant side, we have 2 moles of gas. On our product side, we have 1 mole. Okay, so here we have more entropy. On the product side, we have less. So we're going towards a more ordered chain or more ordered system. So we would expect our delta S and the direction enthalpy is taking is negative. Okay, that doesn't mean that entropy is a negative value. It means the direction entropy is taking. So you can find these values in table 12. So C2H4 is 220 joules per Kelvin per mole. H2 is 131. C2H6 is 230. I gave you a very simple one. So if we had any coefficients in front of these compounds, make sure you multiply your entropy by that value, just like we did with delta H of formation. Okay? So now we have our delta S of reaction. And that's going to equal the summation of your delta S of your products. There's only one. Again, I gave you an easy one. So 230 minus the summation of your delta S of your reactants. And there's 2 of those there. So 220 plus 131. So you get negative 121 joules per Kelvin per mole. Hey, we predicted a negative number. Yay, we did it right? Okay, because we're going to end up working with delta H, and delta H is in kilojoules, let's just make it a habit to finish this number out. So negative 0.121 kilojoules per Kelvin per mole. And that way you're always going to be in the same unit as needed for delta H of formation.